Hello there, folks. Well, welcome back to Petrophysics Rocks. It's fair to say, I think, that you can expect a bit of a flurry of content from me over the next few weeks as I resurrect my old presentations from my website here to my new YouTube channel, so that YouTube can curate things for me. This particular presentation, Pickett Plot Essentials, was done as part of our Petrophysics for Dummies seminar. We had a delightful evening in Aberdeen with teams of 4 or 5 people competing against each other for the Petrophysics for Dummies prize to calculate the correct size of the oil field discovery that we were making. We had, as I say, we had about 130 people there, but there was no way in that environment we were going to be able to get people to get their slide rules out or even their calculators and calculate water saturations from porosity, resistivity, etc. So what I did is I put together this graphical solution to Archie. It's called a Pickett Plot, and you're able to go in here and with a porosity and a resistivity, and then read off a water saturation, which was much more achievable for the people that were there. As I say, it's a graphical solution of Archie, which reminds me, if you have the opportunity, would you like to click down in the link below to the Archie Aberdeen Royal Infirmary Children's Hospital link? If you click through, you'll get to my Just Giving page. I'm sure they'd appreciate any donation, large or small. They do a great job over there, and this graphical solution to the Archie equation, which is so fundamental to all of us petrophysicists, I'm sure they'd appreciate your largesse, as it were. And whilst you're down there, if you could maybe click on the like button and maybe the subscribe button, and go for gold, and maybe stick a comment in there about how useful you find this this kind of thing, or even just as I say, let me know where you're listening from, and maybe if you have any ideas for future presentations once I start getting back into the original content again. I'll put that to the front of the list, as it were. Okay, so let's crack on and get to Pickett Plot Essentials. As I say, I'll hand over to my 2010 self now, and I hope you'll find some of the concepts in here quite useful. Not only is it just a simple read off of the water saturation, but hopefully it'll give you a bit of an insight into the Archie calculation, the Archie equation, and what some of these terms mean in real world. Well, not in real world, but in graphical terms, at least, to give you a better gut feel about what goes on in Archie space. Okay, thanks a lot for your attention, and I hope to catch you soon on Petrophysics Rocks. Cheers.
Welcome to Pickett Plot Essentials, the graphical Archie solution. I put these slides together to support our Petrophysics for Dummies seminar, where I wanted people in their teams to be able to calculate water saturation without recourse to calculators or even slide rules if they'd happened to have brought them along. So if I just go through the outline of the presentation, I've added a few more little extras that hopefully will make it a little bit more applicable and more of wider use. But what I'd like to talk about today is the Archie equation itself. I'll just briefly go through the Archie equation. Then I'm going to get on to the Pickett plot itself. And there are a couple of elements that I'd like to discuss about the Pickett plot. There are the M cementation factor. And I'll show you how that behaves, what that looks like in plot space, in the Pickett plot space, and I'll try and give you a flavour for what that means in terms of pore space behaviour, what's going on in the pores that controls this cementation factor behaviour. And also I'll touch on some core data measurements that we make. This formation resistivity factor is a direct core measurement which we make to calculate this M cementation factor directly. Also, I'll talk about the N saturation exponent, and I'll show you what that looks like on the Pickett plot space and how that affects things. And I'll also try and give you a flavour of what that means in the pore space, what's going on in the pore space to cause that behaviour. And also I'll again touch on some direct core data measurements where we measure a thing called the formation resistivity index to calculate the saturation exponent N directly. And finally I'll finish off with a real-world log data example. So here is the Archie equation. May look a little bit daunting, but I've listed all of the coefficients and parameters down here, what they mean. And one of the things I'd like to point out is that in the pore space of a rock, we have 100% fluid, be it gas, oil or liquid. And if we can calculate the water fraction part of it, this SW term, the saturation of water term, we can infer the hydrocarbon saturation, because 1 minus the water saturation is the hydrocarbon saturation, be it oil or gas. So that's what we're primarily interested in, but we get at it by calculating this water saturation. One of the things that I'd like to point out, I guess, is that if the top half of this equation is low, is small, or the bottom half of this equation is a big number, then this SW, the water saturation, will be low. So increasing oil saturation, the thing that we're interested in, what do we need to do to get to high oil saturation or low water saturation? We can get this low water saturation if the salinity of RW, the resistivity of the formation water, is high. Then it conducts electricity well, and the resistivity is low, so this term becomes small, and this term becomes big, and therefore the SW term becomes small. If the porosity term is high, this porosity term here, then this term at the bottom becomes big, and again the SW becomes small. Resistivity, true resistivity measured in the formation, if that's a high number, then again this bottom term is high and the SW is low. For completeness, we also get higher oil saturations, lower water saturations if M is low, because we're raising this fractional number here, porosity, this Greek letter phi used for porosity. If we raise that to a low number, the resultant number here is actually high, and therefore we get a low water saturation over on this side of the equation. It sounds a bit counterintuitive, I know, but trust me, if you have a look at it in Excel, you can work it out. And convert as also, if N is low as well, then this saturation term will be lower. In fact, if I just do that for you, that might help you code it up into Excel a little bit more easily. All I've done is the same equation, I've just rearranged it slightly to take the nth root of both sides. All we need to do is raise this term to the reciprocal of n. I've put these brackets here just to remind you that if you code this up in Excel, it's important to put these brackets up first before you raise this exponent. Otherwise you'll get into all sorts of trouble. So if you plug this into Excel and then raise it to 1 over n, then that's the same as taking the nth root of both sides, and you'll get a direct calculation of SW for you. So that might be a little bit easier for you to code up into Excel. Now you can imagine that putting an equation like that up in front of 130 people in teams of 6 at a pub quiz environment might not be the most sensible way of getting a sensible water saturation calculation out of them. So much as we love the Archie equation, it was, I thought, sensible to go the graphical approach so that people could just essentially use a chart and look up a water saturation calculation. So here we have the Pickett plot. The Pickett plot plots porosity, in this case on the y-axis, against resistivity. Now, Pickett plots come in a number of formats, and sometimes you'll see the axes plotted the other way around. But in this particular set of plots I'm going to take you through, porosity is on the y-axis, with porosity increasing. It's a logarithmic scale, as you can see, and up here at the top is 100% porosity. Now, what is 100% porosity? Well, that's just a beaker of water, if you like. That's the fluid. There's no rock in the way. That's just 100% fluid. So what are we measuring up here on the resistivity? So this resistivity at 100% porosity is the resistivity of the fluid. And this resistivity axis, as you can see, increases from left to right. So if we want to know what is the resistivity of our fluid, well, first of all, it depends on a couple of factors. It's no good just quoting a resistivity, in this case 0.02501 meters. What does that mean? Well, it's highly dependent. It depends on what temperature you're measuring it at and what salinity you have. So in this case, if we say that, if you remember your school physics, a fluid conducts electricity if it's saltier, if it's got more salinity in it. More saline waters conduct electricity better, and we have a lower resistivity. Similarly, if we have a hotter temperature, resistivity decreases as well, because hotter fluids conduct electricity more easily, so therefore the resistivity again decreases. So the interplay between between temperature and salinity is really what controls resistivity. If we fix the temperatures here, so here I've said that the temperature is 297 degrees Fahrenheit and the salinity is 75,000 ppm, then that's what our resistivity is. 0.025 meters at 297 degrees Fahrenheit is equivalent to 75,000 parts per million total dissolved chlorides. That's the salinity measurement. So that's this apparent RW term on the top of this equation here. So we know the salinity of our water, and geologically speaking, in most of the reservoirs we work in, we know whether we're near salt domes, and we have a fair idea of what the salinity of our reservoirs is. So we can fix that point for the purposes of this, and then let's introduce some rock into the equation. So let's decrease the porosity. So we'll come down and we'll decrease the porosity, putting rock in the way. And as we put more and more rock in and the porosity decreases, the resistivity, as you might expect, increases. And the rate of change of resistivity increase is this Archie M exponent, this cementation factor. And let me just get my cursor over here. So this rate of resistivity increase, the gradient of that is this M, Archie M gradient exponent. The harder the work that we have to do, the more resistive, the higher the resistivity. So if we keep this porosity fixed and we increase the work rate, if you like, this is a higher M, a higher cementation of 2.7. What I'm saying here is that for the same amount of porosity, we've had to work a lot harder to get here. So the rate of change of resistivity is higher. So this is a higher Archie M gradient. So that's harder work. For any given decrease in porosity, we've had to work a lot harder. The resistivity has increased much more. Okay, and we could continue down that trend, again decreasing the porosity, and we squeeze into tighter and tighter rock, and what that means is that there's less bulk fluid to conduct the electricity, less fluid conductance, and so therefore the resistivity increases because the bulk volume of fluid decreases. Okay, so going back to mid case here, if you like, let's go and have a look at what's happening in the pore space. Some people like to look at these cross plots and they get all they need from the cross plots, but let's bear in mind what's happening in the pore space. So I just go and have a look over here. So a bit of revision. There we have our fluid, 100% porosity. The thing that's controlling the resistivity, or the ease of which current can flow through this pore space, is the salinity and the temperature. Once again, if we fix that, we know what the fluid is and we know what its temperature is, therefore we know its salinity, or any one of those things we can work out. So if we put some rock in the way, you can see that the current path is restricted, the resistivity is increasing, and here we are, we're coming down this pretty standard line. Typically, if you use an M of 2, if you don't know anything else, you won't be too far out most times. So we just progressively increase the amount of rock in the way, i.e. decrease the porosity, and the resistivity, the current pathways are restricted, and you can see that the resistivity increases. And again, once we get to lower porosities, the current is restricted further. If I just quickly back through that, as we get more and more rock, it gets more and more difficult for the current to flow through. Now you could imagine a situation where we've got current flowing through a rock, and here it's back to our base case again, or 20% porosity rock. Now if these grains were smoother or more well sorted, you might imagine that it might be easier to flow current through them. So let's just round them off and sort them out a bit. There you go. And it becomes a little bit easier for current to flow through there, and the M factor drops, for any given bit of porosity, it's a little bit easier to flow. So the M factor drops. Let's just toggle between the two, just make them a bit smoother, a bit more well sorted. I'm trying to keep the porosity the same, diagrammatically speaking, so any of you with image analysis software who fancy calculating whether I've done a good job, then you've probably got more time on your hands than even I have for doing this sort of thing. So the idea is here, I'm trying to show you that keeping the porosity the same and just changing the grains changes the current pathways. And here I've put some irregular or perhaps some cemented grains in here. You could imagine that these are either poorly sorted or more immature sandstone, more angular pathways, or perhaps some of these are overgrowths and various cementation factors going on here. It restricts the current flow, and our M factor has increased further. So if I toggle back between those two, you see it's more difficult for current to flow through here. It's more difficult for current to flow through here than it is through the better sorted, more rounded grains. Okay, and that's what controls our Archie M cementation factor. Now, of course, we can measure this data on core directly. Now, one of the things that may have been a bit misleading about my smiley faces as they progress their way down the Pickett Plots, you might have got the impression that I'm somehow injecting water or injecting rock or something, and we're making these measurements through a series of injections. But what we're actually doing in M space, if you like, is actually taking a series of plugs, series of measurements at various porosities, and fully saturating them with water, so they've all got 100% water in them, and then we measure the resistivity of them. And when we do this on core, we measure what's called the formation resistivity factor. And the formation resistivity factor is the resistivity of 100% saturated rock, i.e. the resistivity of these plugs with 100% water in them, over the resistivity of the saturating fluid. So it's, if you like, it's the ratio the rock has. It's the amount of resistivity that the rock increases the resistivity by over and above the saturating RW resistivity of the water. And the important thing on core measurements is that we know what the saturant salinity is, because we made it in a beaker and we put it into the rock, so we know what the salinity of the water is, so that point becomes fixed. We know what that is, and so the ratio of the resistivity of that fluid to the saturated rock becomes this formation resistivity factor. And here you can see 7 plugs, all of varying porosity, from what's that, about 13% porosity up to 28% porosity, and we've measured this resistivity on it, and we can draw a straight line through it, and we know what our water saturation or water salinity is, and we have a certain gradient here. The slope of this line is our Archie M gradient again, because FRF, formation resistivity factor, is related to porosity by this equation here, this A term over porosity raised to the power M, where this A term is sometimes called a tortuosity factor, but really it's just a resistivity modifier, and this M cementation factor that we've come across already from the Pickett plots. And the sharp-eyed amongst you will realize that this equation here in log space is merely the equation of a straight line. Log FRF is the y equals mx plus c part of the business. So that's all that this exponent is, the equation of this straight line with this m gradient. It's actually a negative m, but we won't worry about that just now. So there we have it, and m is equal to 1.96. So I told you that if you use 2, you're not going to be too far out of the story. However, I guess one of the things that we can also do with core data is that if we know that, say, 3 of those plugs come from a particular facies, particularly they might be geologically related, you might say that that facies actually has a higher m of 2.8. Now we know that the salinity of the water hasn't changed, and so we've got a modified A term, and so we know what the resistivity of the fluid is at 100% porosity, and so to get that to calculate out right, we have to calculate this A factor, this resistivity modifier, to be able to match the known saturant resistivity at 100% porosity. Similarly, if these other 3 points here are in another facies, we might have another set of rock with a different M and A values as well. And so these trends may vary by facies. And so personally, I'm not averse to drawing lines through the cloud of data. I'd rather be drawing trends through defined over geologically meaningful porosity ranges. I'm not really that fussed what happens that goes on between 70 or 80% porosity, or 90% porosity, or 100% porosity, because that doesn't tend to occur in nature. So I'm not averse to extrapolating data trends from through the clouds and into the 100% realm, and using A's not equal to 1. Some people just like to keep A fixed at 1. I'd rather let the data talk. And typically a good example of this is some work done by Winsauer et al. in the early 50s. They came up with what's termed the humble relationship, where empirically a bunch of soft crumbly sands, I think they describe them as, have an A of 0.62 and an M of 2.15. So that's quite a common empirical number as well. So if you're out there with your cross plots trying to evaluate a wildcat area, then you could either use A of 1 and M of 2, or you could give humble a go and see if you got a better answer there. So that's the extra information that you can get from core. Because the RW is absolutely known, you can start to get a true handle on what this A factor is, as well as your M factor. And one of the things to bear in mind is if I toggle back through these plots, is that they don't vary independently. So generally, if M changes, then so does A. Okay, so there we are back at our base case with our 100% water saturated rock at a certain resistivity. So here we are at our 20 or 18% porosity rock at a certain resistivity. What happens if we put oil into the system? So we keep the porosity the same and we put some oil into the system. Well, obviously, because the oil is a non-conductor, the resistivity will increase by some amount. And if we can calibrate the amount of resistivity increase to the amount of oil saturation, we can scale that in terms of saturation. So in this particular example, I put some oil in the system at the same porosity, and this N measurement, this saturation exponent, which appears here, it quantifies the scale to saturation. So here, for example, this particular resistivity in this particular setup with this N is 20% saturation, 20% water saturation, or 80% hydrocarbon saturation. Now, depending on the amount of work that has to be done in the pore space, we could get the same saturation, but in a slightly more perhaps oil-wet rock. To get that same amount of water saturation or that same amount of oil saturation, and we have to work a little bit harder. And we can say that the resistivity we require here, for example, we need 100 ohm meters, gives us the 20% water saturation. If we go back to that example here, we were getting 20% water saturation, and we only had to work as hard as 25 ohm meters. So that is a function of the rock, but it's actually a function of the fluids within a rock. So let's go and have a look what's going on in the pore space that controls the spacing on these lines, if you like, this calibration to saturation. Here we are with our conductive pathways at our 20% rock. You can see that the current is flowing through here quite nicely, and if I plot on this is a formation resistivity index plot, something that we measure on core data. We plot the formation resistivity index against fractional brine saturation. So here we are at 100% brine saturated, so there we're up at this end of the plot. And if we define this formation resistivity index, it's the measured rock resistivity over the resistivity of the rock when it's 100% saturated. So those are all our Archie points, if you like, by definite. Our Archie M points on our previous Pickett plot, our water-bearing points. Here they are, and the ratio, of course, is 1. The resistivity of the rock is the same as the resistivity of the rock at 100% water saturation, because that's where we are. So we start out here, and if we put a bit of oil into the pore space, you can see I've put blobs of oil. It restricts the current flow. The resistivity index, formation resistivity index, the resistivity itself increases. This remains fixed, of course. That's the reference point. And of course, formation resistivity increases. And it increases along this line here. And once again, you'll notice that, if you like, is how hard is the work that has to be done to increase the resistivity. So this increases with this gradient, and in this case n of 2. So let me put a little bit more oil in. The resistivity increases further. This resistivity index ratio increases, and we follow this pathway up on this n equals 2 line. Now let's say that if we put something in the pore space, we try and keep the saturation the same. Let's put some microporosity around these pore grains, or perhaps some conductive clays, something to ease the current pathway, so it becomes a little bit easier for current to flow through for the same saturation. If I toggle between those two, you can see, or you can imagine that diagrammatically I've put some microporosity in, or some where there are some clays, conductive clays, that allow the conductivity an easier pathway, and the resistivity drops a little bit for the same saturation, and therefore it becomes a little bit easier to flow. Now, in actual fact, what you often see is something at these high water saturations that follows this n of 2 line, and then as the saturation decreases further, you see a sort of a curvature on these points, because the effect of this microporosity, or these conductive clay areas, becomes progressively more and more dominant, so it's slightly non-linear. But in general, the point I'm trying to get across here is that you can see that you're, if you like, short-circuiting some of the pathways and making it a little bit easier for current to flow, and so the n decreases. Conversely, if I make it an oil-wet system, now what I've done here is I've just, instead of water being next to the grains, floating all around the grains with blobs of oil in the center of the pore space, in an oil-wet rock, the oil phase is dominant and is around most of the grains, and you have, if you like, blobs of water in the pore space. And here you can obviously see that it's a lot more difficult for current to get through. They've got to find connective pathways through the through the water saturation to flow from one end to the other. So therefore, in an oil-wet rock, we lose those conductive pathways and we get a more difficult current flow. So for the same saturation, you see, we're just moving up and down this saturation axis here. You could imagine a situation whereby the work is a lot harder for the conductivity to get through. And again, those of you with image analysis software, please try and resist the urge to work out whether that was really the same saturation. I think hopefully you get the point. Here is an example of some real-world N measurements on a number of core plugs, and here we are making a series of measurements on a single core plug. That's differing from the FRF measurements, which are single measurements on single plugs. Here in our N world, we are making a number of measurements on single plugs, so we're taking a single plug and we're taking it through various desaturation methods. And here are some examples. You can see that there's quite a wide scatter in potential behavior on an individual plug basis as we take that plug and slowly and progressively desaturate it. And we have a range of N measurements, and at the end of the day we might take a composite N of 2.22 in this case as an average of all of those behaviors. But clearly in real life you would look at what was controlling that spread, and you would try and work out whether you had any Fash's dependency on that, or whether there was something peculiar that you needed to understand about your rock to explain this range in N values. Okay, so that's how hopefully you can see now that this, if we go back to this one, that's how this N is increasing. That saturation exponent is really the degree of work that has to be done because of the amount of fluid, hydrocarbon fluid in the way, and the contributing factors of current pathways in the presence of oil. That's what controls that calibration. Okay, so in summary, for my petrophysical seminar for dummies, what I wanted the guys on the table to be able to do was just simply read off a porosity, come in here with a porosity, measure a resistivity from the log, and come in here and then be able to come down and calculate a 55% water saturation, or come into the plot and be able to read off the water saturation for their exercise. But one of the things that Dick Pickett emphasized a lot on this methodology was really about a way of defining trends, and his paper reference at the beginning there was really all about looking at trends in data. It wasn't just a way of calculating a water saturation given in a chart-like fashion. The real value of this stuff is when you look at real data, lots of log data, and try and pick out trends in the data. So here is some real log data, typical petrophysicist crossplot you might think, but bearing in mind what you now know, if we have a look at the southwest portion of this plot, you can see that there is a sort of a linear trend down here that might define the lowest resistivity, the most conductive pathway through this log data set. And indeed we can put a line through there with our Archie M, so we can put a line to the southwest corner, the most conductive parts, and say, well, that's most likely to be the 100% water bearing rock. And indeed up here you'll have the hydrocarbon signal coming through, so for the same porosity, elevated resistivity, that's hydrocarbon. But down here on this southwest quadrant, that's the water bearing rock behavior. And we can use this type of thing to extrapolate these lines through, and we can say, oh yes, look, at 100% porosity, what's the apparent RW? Okay, it's 0.1071, which is 19.6, so 20,000 parts per million chlorides water. And then petrophysicists might be able to sense check that against, well, does that sound reasonable to me? Is that what I expect for this geological basin? Etc., etc. And in this case, trust me, it is what we expect. 20,000 parts per million is what we see in our northern North Sea Brent reservoirs, for example. And we can get some N measurements on there, and we can scale that to saturation, so we can go in here. This is the 100% water line that we've talked about, and here are the saturations progressively. Oil saturation is progressively increasing, water saturation is progressively decreasing. So here is this rock is about 20% water saturated, 80% oil saturated, and here less than 10% water saturation. Really good quality, high resistivity rock. Now, one of the things that obviously I've mentioned before, we've got the core data, and here from core measurements on this rock, we know in fact that the A and the M factor are slightly different. In fact, I've kept the RW the same because this is the RW of the field water resistivity. If I just toggle between these two, this is what you might do from a Pickett plot analysis, where you're extrapolating a water salinity. And here, if we have core data, I can employ the A and the M from core data directly and overlay that. It's a bit of a moot point whether that gives you a better feel for saturation, a better calculation of saturation in this particular case. You can see they're both within the bounds of possibility, but clearly you've made some measurement on some core, you spent some money doing that, so it would be probably remiss of you not to use it, and it would make 1 or 2 saturation units difference to just eyeballing it. So given that this core data is valid, then you could use an M of 1.92 in this case, and an A of 0.69 as well from your core data. So finally, in summary, what I hope I've shown is that Pickett plots are a useful way to graphically calculate water saturation. If you're ever running a seminar like that, it's a handy way of providing people with charts to be able to back calculate a water saturation given a resistivity and a porosity. We often use Pickett plots to extrapolate a formation water resistivity. So if your petrophysicist says, oh yes, I calculated the water salinity by Pickett plot method, then now you know what he means. He's basically extrapolating the data to intercept the 100% porosity point at the fluid resistivity. And does that make sense to you as a geologist? Maybe. And finally, the trends in the data are very useful, potentially in giving us insights into other reservoir properties, or you can get a feel for the degree of work that has to be done for the current to flow through your rock. So you get a feel for this cementation, or sometimes called a shape factor, a sorting factor if you like. So that can give you some insights into reservoir quality as well. I've droned on quite a lot. I do apologize for that. It was supposed to be a quick and dirty, but the problem is once you enter discussions about Archie, the petrophysical holy grail, you have to cover a lot of ground just to make sure that you don't miss anything out. And I probably have done that as well. I do apologize for any omissions, and I wish you well in using it. Okay, thank you very much.